So behavior trees are an extremely important part of enemy or NPC AIs in video games. If you don't know what a behavior tree is, I have a really basic one here that I'll go over in a second, but it's basically a tree-like structure that is composed of different nodes, and the way you arrange it kind of dictates how the behavior tree, or like AI brain, I guess you could call it, works. And I prefer using them over state machines in most cases because they are a lot more modular than state machines. I know it's probably hard to believe right now, but I'll get into all that. So before we get started, I am using a behavior tree plugin, and this is by BitBrain, who is a fellow YouTuber. And I'm going to put the link to all of the resources I use in the video in the description. Head over to the GitHub page for Behave, and this is a Godot add-on. I think it's also in the asset library if you want to do it that way, but you can just click on this code button and download the zip file. Now, once the zip file is downloaded, you just want to extract all the contents, and you want to drag this add-ons folder and also the script templates folder into your Godot project directory. So you can see in the left here, I have my add-ons folder and I have the Behave add-on. And then the script templates folder doesn't show up, but if you want like automatically generated templates for your Behave nodes, which we'll be making later on, then I would recommend just throwing that in your project files. And then once you have the add-on actually in your project, you have to go up to project settings and go to the plugins tab and just make sure that Behave is enabled. And from there, you might have to restart, but everything should be working correctly. Now, a really quick note, if you do look on the GitHub page, there's like an official wiki for the Behave add-on, and this completely messed up my camera because it's white mode, but this will have like all the resources if you're wondering about any specific nodes. I'm going to cover most of these in this video, but it's going to be a lot, so I might have to do a part 2. So to actually create our own behavior tree, I'm going to be using this enemy scene I made, and it's extremely basic. You can copy this code if you want, but it just has a health, a speed, and then it has some basic code for actually moving, which I will also get to later, but this is where we're going to be putting our behavior tree. So I'm going to actually delete this one I've made previously. And whenever you want to create a new brain or like a behavior tree for an entity, you would click on your add node button, and we want to scroll all the way down until you see this behave tree node. Now, every single behavior tree has to start with this node. Now, whenever you add this node, you have to assign a target, which is essentially what is the object that we are like controlling with this brain. So if I go into the inspector, you can just assign the actor node path to the root, which is my enemy. And from here, everything should be set up correctly. Now, really briefly, a behavior tree is basically just going to run through all of its child nodes every single frame of the game and process their specific code. It just calls like a tick function on every single node. You can change the tick rate if you want. If you want to optimize your game further, this might be something to look into, like reducing this as they get further away from the player, or even just in general, but that's just a basic note. So now that our behavior tree is set up, we need it to execute some specific nodes. And first we want to figure out what is our enemy supposed to do. So if I run my example scene here, I basically have a way to move around the player. And then if I hit space, it's going to damage the enemy. And for this first behavior tree, I want the enemy to follow my player. But if at any point the enemy's HP goes below, let's say 30%, I want the enemy to start retreating away from the player. So to set that up, we need the first component of our behavior tree, which is typically a sequence. Now, if you click on the add button and you go to this behave nodes section, you can see that we have a group called composite. Now, the composite like node class is kind of the first type of behave node that we're going to be looking at. And to explain it super briefly, it's a node that kind of defines specific logic for how its children nodes are executed. So for example, we have something called a sequence composite. If we added this into our scene and we added a bunch of action leaves, I'll get to these in a second, but this sequence composite would say we want to execute all of the children nodes in sequence, right? So we would start with the top one. Once this has completed, we go to the next one and the next one and the next one. So if you had a sequence of actions, this would be a perfect type of composite node to use. Now, looking at some of the other options here, we have a selector composite. Now, at a very base level, a selector essentially picks one of its child nodes to execute. And typically the child nodes are sequences themselves. So you might have a selector with a few different sequences inside of it, and the selector would pick one to use. An example would be like if you had a sequence for playing a death animation or something like that, a sequence for attacking the player, those would be in a selector, and the selector would first look at, hey, do we want to execute the death animation, which might only run if the health is 0, right? Or do we want to execute the attack, which might only run if the attack's not on cooldown? So a selector is good for picking one child node to run. And then we have a couple other really cool ones here. So like a parallel, we have a randomizer. I will note once again, if you do get stuck, the Wikipedia has a lot more information that I'll be explaining in this video, so you can really read more into the specific nodes there. But going back to like what we want this enemy to do, I said it would either move towards the player or away from the player depending on a condition. So that's basically a selector composite. So I'm going to select the selector composite node, and this is going to be our first node in the behavior tree. Now from here, the behavior tree is going to start running and process our selector, which needs to pick another child node to actually run. And right here is now when we need to actually execute some code. So in a behavior tree, that brings us to the next part of a behavior tree, which is an action leaf or a condition leaf. They're pretty similar, and you can also find them in the same behave node section. But an action leaf is basically for performing an action or usually just running like a specific function or something like that. And a condition leaf is for checking a condition. If that condition returns false, usually it stops the behavior tree at that point and tries to execute a different part of the behavior tree, which we'll also get to later. Some examples would be an action leaf might be for executing an attack, and a condition leaf might be for checking if that attack is off cooldown. So in this case, the first thing we want to do is check the HP status of the enemy, because if it's less than 30%, we want to run away from the player. So I'm going to add a new condition leaf, and by default, it has the base condition leaf class attached to it. We actually want to extend this class and make our own code for this condition. So I'm going to click on this little extend script button here, and I'm going to call this leaf HP less than underscore BH. I like to add this BH at the end of my behavior tree scripts because it kind of signals that they're part of this plugin. It just for organization, I guess. And if you have the templates folder, you can use the built-in behave node template. If we click on create, you can see that we've made a new script that has a tick function, and this is basically where the bulk of our code is going to be. So really quick prerequisite for creating a new behave node, you have to add the at tool annotation to the top of the script, and then we have to define the body for this tick function because we're overriding it from the parent class. We're not going to use the Blackboard right now, so I'm going to actually add an underscore here, but you can see we have the tick function, which is passing the actor directly to this node. And if you remember what I said earlier about the tick is basically the process. So like when this node is called to process from the behave tree, it'll be represented by this tick function. And the actor node is just what we've assigned as the reference in the inspector. So the enemy, which is the root. Now, just for the sake of the tutorial, I've pasted in some code here that will check the HP percentage of the enemy, which is our root node. But this is essentially how your condition leaves would look. So I've added an export variable at the top, which allows you to assign like a specific parameter to the specific condition leaf. That way we can reuse this component in multiple places. And all I'm doing is when this node processes, so in the tick function, if we don't have an actor, we're obviously going to stop processing. Otherwise, we're going to get the health percentage of the actor by using its current health and the max health. And then if the actor health percentage is smaller than the health percentage that we've defined on this specific node, so in this case, I'm going to set this to like 30, which is what I said before, then we're going to return success. Otherwise, we'll return failure. Now, the only thing that might look unique to you is this return failure and return success thing. This will basically signal back to the behavior tree how this node was processed. And this is like the bones of how a behavior tree works, is what a condition leaf or an action leaf returns. So there are 3 different return types. I'm only using 2 here. The first one is going to be failure. Obviously, if any node in your scene tree returns failure, the behavior tree is going to say, all right, like that node cannot be processed. So it's going to go back and try to process something else. In the case of a selector, if I had 2 different nodes here, the behavior tree will try to process the selector, which is obviously going to work because it's the only child node we have. And the selector is going to go through and say, all right, here's my first node. Can this be processed? If this node returns failure, it's going to go and try to process this next node. And if it returned failure again, just like its sibling, then the selector would say, all right, we can't process any of these children. So the selector would return failure. And then from there, if we had any other nodes, like as a sibling of the selector composite, the behavior tree would continue to try and process those ones. It's basically just going to continue trying to process nodes until it hits something that fails or something that's currently running. And apart from the failure and success return types, that's the third one that I didn't mention yet, which is the running. So you'd return running just by typing like this. And for an example quick, if the selector tried to process this condition leaf and it returned running, then the selector would actually just wait until this node has either returned failure or success to actually continue through the scene tree. So usually running is reserved for times where you need to wait until a process is complete or until a specific condition is met to actually continue through the behavior tree. They're kind of tedious to work with because a lot of times it will pause the rest of your tree. So you can structure it in a way that it like breaks out of certain loops that may occur. But in general, just be careful with the running return type. Hopefully that explanation made sense. If you have any questions, still ask them in the comments and I'll try to explain. But basically, this condition leaf will now return success if our enemy's HP is less than 30%. Otherwise, it will return failure. So we can use this in our behavior tree. I'm going to delete this other one that I made, and we're making sure that the script that we've just created is attached to this node, and I'll rename this to health less than 30%. And a really quick tip that I think is super cool, because this is a tool node, you could technically make a system in each one of your condition and action leaves that automatically renames the node based on the parameters. It could save some time and it would be kind of cool, but I don't think it's necessary at all. So from here, if the health is less than 30%, we want to start retreating from the player. So to do that, that would be an action node, like I mentioned before, and this is going to be under the leaf section, and we're going to add a new action node, and I'm going to call this one retreat from player. Now, just like before, I've pre-made a script for the movement code that I'm going to attach to this node. If you want to make your own script, you can obviously extend the class like we did before, but this has some interesting movement code. So you might be tempted to put your movement code directly inside of the tick function. Technically, the behave tree is on the physics process, so you could call move and slide inside of the tick function, I guess, but that's not recommended. I'm sure a lot of you want to use the composition approach for game development, and containing your movement code inside of a random behavior tree action leaf is kind of weird. So what I like to do is split my movement code off into an entirely separate module. So I basically just have a movement module, and then the action leaf would basically just be controlling that module. Now in this example, I kind of merged the movement component into the enemy script to make things a bit easier. But really all this code does is if we want to move away from the target, we're going to set the move direction of the movement module or the enemy actor to move away from the target. And if the type is move to target, we're literally just doing the opposite of that. But the main thing to note is we're not actually moving the enemy actor from this tick function. We're simply assigning the direction that we want it to move. And then your movement component, which I'm realizing I didn't set that up in this tutorial, but this would be like a movement component that would actually apply the motion to the entity. That way you're like retaining your modularity in your game, which I think is very important. So assigning the parameters of this node, retreat from player. If the health is less than 30%, we want to set the movement type to away from target. That way we're retreating from the player. Now, if you're paying attention, you might have noticed the issue with this current behavior tree we have. So when I process this behavior tree, it's going to run the selector, which is going to pick one of its children to run. And because health less than 30% and retreat from player are not exactly attached in the same like sequence, they're not going to be associated with each other. So we're either going to run a condition or retreat from the player. We want to just bundle those together, and we can use the sequence node like I was talking about before. So I'm going to add a sequence composite node and basically just put the action and condition leaf as a child of this. And now when we run the selector, it's going to first check, hey, can this sequence node run? And the sequence is going to go in order. So from top to bottom, it will say, hey, is the health less than 30%? If it is, then it's going to continue and retreat from the player. If it's not, then this will return failure, which will tell the sequence to return failure, which will then tell the selector the sequence can't run, and then we'll continue to the next node. And the next node, I'm literally just going to duplicate my movement node, and we're going to drag this outside of the sequence. So it's a sibling of the sequence. I'm going to call this one move at player. And I'm just going to change the movement type to target. And this way, hopefully you understand the logic here. So we're selecting either the sequence or the move at player, and the retreat from player action leaf can obviously only run if this returns success, which is linked to the health percentage. So there are a couple like optimization things I want to mention in a second, but let's try this out. So I've put this enemy in a scene with the player, and I'm actually going to embed this into the editor just so that we can see a bit better, because something that's really cool about Behave is if you go into the debugger panel at the bottom, you can actually go over to the right and there should be this behave tab. If you click on this, you can see kind of like a live feed of all the behavior trees in your scene and what they're currently doing. So I like to click on this little icon just to make it horizontal, but you can see that my behavior tree is running the selector, which is returning success because it has found a child that it can run. But you're also going to note that the first thing it tried to run was the sequence, which obviously returned failure as soon as we hit the condition leaf because our health was not less than 30%. So let's try to get the health less than 30%, and you can see this update live. So if I hit space and we go right down to below 30, you can see that we swapped over because this is returning success. We can now run this retreat from player action leaf and the enemy is now running away, which is super cool. So from here, there are two more like big concepts that we need to cover about behavior trees. The first one is going to be decorators, which are super simple. They're basically what they sound like. So if you go to the behave node section, you can see we have this decorator section, and these are nodes that you can basically attach to other nodes to change what they return. So the most useful one, in my opinion, is probably the inverter, and this would basically just flip the return type of whatever node it's attached to. So let's say for the health less than 30%. Usually this would return true if the health is less than 30%. But if we put it as a child of this inverter decorator, we could call this inverter health not less than 30%. And that's because it's flipping the return type. So rather than returning true when health is less than 30, we're now going to be returning false, which obviously doesn't make sense here because we could just flip these nodes around and it would do the same thing. But when you have more advanced behavior trees, you're going to be using these all the time. Some of the other useful ones are like the cooldown, which makes it really easy to use, like a timer system. Also the delay decorator, the until fail decorator. They're all pretty easy to figure out based on their name, but I would just look through all the decorators and composites and also read the docs just to know what tools you have at your disposal. Now, the last thing I want to mention in this video is the final part of a behavior tree, which is used most of the time, and it's called the Blackboard, which you might have seen on the inspector panel. If you click on the behavior tree, we have this Blackboard, which is assigned to a non-existent node, and that's because a behavior tree will automatically generate a Blackboard, and a Blackboard is basically just what it sounds like. It's an object that's essentially just a dictionary, so it stores a bunch of values and keys, and it's great because you can obviously just store data to a Blackboard and then reuse that data and access it between multiple different nodes, because in Godot it's kind of difficult to pass data between nodes a lot of the time without a singleton. So I guess you could think of it that way. A Blackboard's kind of just like a singleton for your behavior tree. So let's try using a Blackboard in this tree. There is one thing I do not like about the code so far inside of the move action leaf, where whenever we process this node inside of the tick function, we are going to search for the target. This line is basically searching through the entire scene tree for the first node in the player group and assigning that to the target, but it's happening every single frame, and it could potentially be happening multiple times a frame depending on how we structured the behavior tree, which is obviously like super inefficient. So this is a perfect place where you'd want to use a Blackboard. The idea is we want to add the target to the Blackboard when the enemy's created and then just reference that value anytime we need it. So I'm going to copy this line and I'm going to do this through the enemy script because it has the ready function right here. And all I need to do is get a reference to my behavior tree. So I can drag, hold control, drop this to get an onReady variable. And down here in the ready function, I'm just going to say behave tree.blackboard.set value, and the key we want to set is the target, and the value is going to be that same thing I had before where I get the tree, get the first node in group player, and that way we're only going to be looking through the tree for the player node a single time initially. Now from the code where we were doing that previously, we want to switch this up a bit. So I'm going to take the underscore away from this Blackboard argument because we're now going to be using it, and because this is being processed by the same behavior tree node, we're going to be using the same Blackboard, but I can literally just say blackboard.getValue, and as long as I provide the same key, which was target, this is going to get the value that I assigned through the enemy script previously here. So this is technically more efficient. Now I did want to note a couple things. So first of all, by default, a behavior tree will initialize its Blackboard. You can also add a Blackboard as a node. So if you search for Blackboard, you could like chuck one in your scene tree like this, and then as long as you access this Blackboard reference and assign it to this behavior tree via the inspector, it would work the same way. And then the other note is we're kind of using like a magic value here, which is the target string. I don't actually like this because we have two instances of this target string, one in here and one in the move action leaf that could be changed at any time and we wouldn't know. So ideally we'd want to reference like one singular data point or like a constant or something. And there's like a bajillion ways to do this. I like to put all of my Blackboard keys as entries of an enum. And because this action leaf could be reused between like players, enemies, NPCs, all sorts of different like types of objects that could have different inheritances, it's good to store that in kind of like its own file. So really quick, I'm just going to set that up where I would have something like Blackboard keys, and this could be whatever you want. I'm just going to inherit from ref counted. All we would need is like a class name called Blackboard keys, and then just an enum called, I guess, keys for now. And we would make a key designated for the target. That way we could just reference this instead of making like a magic string. So the way I would use this is I'd go back into my move, and instead of getting the value of target, I'd get the value from Blackboard keys.keys. Target, and then I would do the same thing back inside of my enemy script here, just like so. And this is a bit longer and sometimes more difficult to read, but this is going to save you a lot of headache if you ended up like doing a typo or something, because previously, like if we had a typo, that would just screw us over. So I prefer doing it this way. I did see some other people using like a resource file that they would load in, which might actually be better because then you're organizing things into like keys that are specific for enemies versus NPCs, but that workflow would just be loading a resource file and then getting either variables or like dictionary entries from it. But in general, just any method that prevents you from typing the keys as bare strings, because that's obviously not great. So aside from that, I think I covered all of the basics for behavior trees. If you have any questions, obviously drop them in the comments. This video is a lot longer than I wanted it to be, so I'll probably just title this like an intro to behavior trees, and hopefully I'll get around to more tutorials. I'll probably make like a part 2 because I do want to show like more advanced topics if you guys are interested. But if you enjoyed the video or you did learn something new, make sure to leave a like and hit that subscribe button. It definitely helps out the channel. And again, leave a comment if you are struggling with these still or have any questions, or you could join the Discord server for help if you'd like. That's just linked in the description, as well as some other various links like my website and whatever. I want to shout out all the current channel supporters. If you're over on Patreon or YouTube members, thank you so much for your support. It's all extremely appreciated, and it obviously really helps support the channel. So thank you guys so much. But with that out of the way, thank you so much for watching the video. If you made it to the end, I hope you have a great week, and I will see you guys in the next one.